I'm going to spend a little extra time in this course talking about climate change. I'll give you the sort of physical science background and the economics of climate change. So that will, in effect, give us an application of the ideas that we've seen earlier about public goods and externalities. And I will also introduce the idea of a public bad, which is just like a public good, except it isn't good. Just incidentally, in the background here, I chose this picture of Thwaites Glacier, which is in West Antarctica. You can't really get a sense of the scale here, but that's a wall of ice about 300 meters high. People who are studying the ice in West Antarctica think that this glacier is probably going to eventually melt. And when it does, it will add about 2 feet to the global sea level. And it's also going to destabilize the glaciers that are behind it, which are then going to slowly slide down into the sea and will eventually add perhaps another 9 feet to sea levels. How long this is going to take, nobody yet knows. But if we just have a look at how these big ice sheets have been melting in recent years, things don't look good. On the left-hand side, we have the change in mass of the Greenland ice sheet, which is melting. The units here are millions of tons of ice being lost per year. And you can see that every year, if 2002 is sort of used as the baseline, every year more and more ice is being lost. I saw a report earlier this month that said that the melting in Greenland just last summer was about 3 times greater than it's been in recent years. And just that melt alone added another 2.2 millimeters to global sea levels. Antarctica is also melting. It's really West Antarctica. East Antarctica last year actually accumulated ice, but the melting is taking place in West Antarctica, where Thwaites Glacier is, incidentally. The ice loss there is doubling every 10 years. The estimate in Greenland is it's doubling every 30 years, although last year's melt might change that. So why is all this happening? Let's think a little bit about the so-called greenhouse effect. So this is just a simple picture that tries to explain it in a couple of diagrams. If we've got a stable system, that's one in which heat is not being built up in the Earth's system, that is, in the atmosphere and on the Earth's surface, both the land surface and the water surface. So in that situation, you have energy coming in from the sun. You have certain gases called greenhouse gases that are helping to trap some of that heat in the atmosphere. So not all of it simply radiates back out into space. Carbon dioxide is the chief greenhouse gas. That's why it's mentioned here. Now, if the level of carbon dioxide goes up, if these greenhouse gases that help to trap heat increase in concentration in the atmosphere, then less heat is going to escape, and heat is going to have to build up inside the Earth's system. So the oceans are going to get warmer, and the Earth's surface is going to warm, and the atmosphere, of course, will also be warmer. Well, one way to think about this, a very useful way to think about this, is this picture of a bathtub. So the analogy here is a very simple one. We've got water flowing into the bathtub. We've got a level of water in the bathtub, and then the bathtub has a drain that takes water out. So we can think of the amount of carbon dioxide and other greenhouse gases as being represented by the level of water in the bathtub. When people burn fossil fuels and emit carbon dioxide into the air, then that's going to add to the stock, that is the amount of carbon dioxide in the atmosphere. So it's going to be a flow that's going into that growing stock. And why is the stock growing? Well, it's growing because the emissions are greater than the net removals. They're greater than the size of the drain. Currently, emissions are about twice as big as net removals. So if this flow into the bathtub is twice the size of net removals, then the level of water in the bathtub is going to be rising. In other words, the concentration of carbon dioxide and greenhouse gases in the atmosphere is going to be going up. The drain, incidentally, is caused by things that absorb these greenhouse gases. If we think about carbon dioxide, a lot of it is being absorbed by the oceans. It becomes carbonic acid in the oceans. On land, carbon dioxide is also absorbed by the soil, by plants as they grow, by trees. So the problem of climate change is coming about because once the Industrial Revolution began and people started getting power from coal and burning coal, and then eventually burning the products of oil, then we end up with these emissions from the burning of fossil fuels and other human activities. So deforestation and so on is going to decrease the size of the removals because now there's fewer trees, and to the extent that that vegetation rots, that's going to add to emissions as well. So what are these greenhouse gases that I'm talking about? Well, carbon dioxide is the principal one, but there are many others. This is a list of them. It's not a chemistry class, so I'm not going to go into it in any great detail. The major ones are methane, CH4 here, and it's particularly important because its ability to trap heat in the atmosphere is a lot bigger than a molecule of carbon dioxide. So if you compare a molecule of methane with the equivalent amount of carbon dioxide, this is about 20 times the heat trapping potential, or what's called the global warming potential. So these numbers here are showing the heat trapping effect of this particular molecule compared to carbon dioxide. A lot of these molecules are used in refrigerants, like refrigerators, air conditioners, things like that, flame retardants, fire extinguishers, and many other uses, a lot of industrial uses. But carbon dioxide, I guess, is the main focus, in part because it's 3/4 of total emissions, and carbon dioxide molecules hang around in the atmosphere for a lot longer than, for example, methane. But methane emissions are significant and they're rising rapidly. So really they shouldn't be ignored. Often when we see the amount of greenhouse gases in the atmosphere described, it's described in terms of carbon dioxide equivalents. So that means that if we add one of these molecules to the atmosphere, that's going to increase the amount of carbon dioxide equivalent by quite a lot, because it's so much more powerful as a heat-trapping gas. Well, the measurements I'm going to show you are going to focus just on carbon dioxide. So let's see what's been going on with the stock of carbon dioxide in the atmosphere. This picture here shows the concentration of carbon dioxide in the atmosphere going back 10,000 years. So I chose 10,000 years because that's the length of time that sort of human civilization as we know it has been busy developing agriculture and fixed settlements. So people stopped being hunters and gatherers around 10 to 15,000 years ago. The amount of carbon dioxide in the atmosphere is measured in parts per million. And you'll note that this particular graph, the horizontal axis, begins at 200, not 0. So what you see here is a very steady, pretty steady level of carbon dioxide in the atmosphere up until the Industrial Revolution began around 1750, at which point, as people started burning coal for energy, the amount of carbon dioxide in the atmosphere started to rise. And you can see it's risen in a spectacular fashion in the last century or so. But this increase, just to draw your attention to the vertical axis, this increase is about a 50% increase compared to pre-industrial times. So about 280 parts per million is the amount that existed before the Industrial Revolution, is now 415 parts per million and increasing. Well, where does this data come from? Mauna Loa, as some of you may know, is an extinct volcano on the island of Hawaii. And there's been a monitoring station there since 1958. Before that, we can figure out what concentration of gases were in the atmosphere by examining what are called ice cores. So these ice cores are ice that has been extracted from drilling down into the Antarctic ice sheet. So these ice sheets formed as a result of falling snow year after year after year for hundreds of thousands of years. And every year, as there's a net addition of snow onto the ice sheet, then the next year a layer of snow is added to that, and the snow eventually gets compacted down and becomes ice. But within that snow, as the ice forms, are little bubbles of air. And scientists have drilled down and have got the technique of extracting those little bubbles of air and examining their content. So we've got estimates of the amount of carbon dioxide in the atmosphere going back at least 800,000 years. Just recently, someone came across some ice that was 2 million years old. But that has yet to be analyzed and published. Well, the basic point is that for this span of time, the last 10,000 years, that human civilization has existed, we've never seen carbon dioxide levels like this. And in fact, carbon dioxide levels have never reached this level in the last 800,000 years, and it's probably been millions of years since they were at this level. Oh, just one quick comment. This little dip here in the 1500s is kind of interesting. There was a paper published earlier this year which explained it. I think probably for the first time. When Europeans came to Central and South America, when the Spanish and the Portuguese arrived there in the 1500s, the diseases that they brought with them, thinking about pandemics, they brought smallpox and measles and other diseases which swept across Central and South America and killed about 90% of the population. So in about 1500, when Columbus arrived in the so-called New World, there were about 60 million people living in Central and South America. That population was reduced to about 6 million by the early 1600s. So all the land that those people had used to grow their crops was taken over by jungle and forests. And that growth, that increase in the size of the drain, if you like, took a measurable amount of carbon dioxide out of the atmosphere and actually cooled the earth for the next century or so. Well, in the next slide, next set of slides, I'm going to go on to examine a more recent experience.